In this lecture, we're going to talk about rockets that fly through the atmosphere. This would include any model rocket that we might build, but it would also include any space launch vehicle as it's launched from the ground. And so we're going to be talking about aerodynamics. We're going to be talking more about the kinds of forces that are exerted on the rocket as it travels through the air. Now let's go back and review the four fundamental forces acting on a rocket in flight. And here they are. Here's our favorite diagram. The first one is thrust. That depends on the rocket motor, how it's firing, the specific impulse of the engine, the rate of consumption of propellant. And then, of course, there's also the weight, which always points downward toward the Earth. And then there are the two aerodynamic forces. There's drag, which we've talked about at some length, and there's lift. And the difference between them is that drag always acts in the direction opposite to the velocity of the rocket, whereas lift always acts in a direction perpendicular to the rocket. So today, we're going to talk about lift. Now, lift depends on something called the angle of attack. So if we have a rocket flying so that the line of its motion is straight along its center line, in a nice symmetric rocket here, then we say that the angle of attack of that rocket is 0. And if that were the case, there's no lift on the rocket because there's no reason for the lift to be in one direction other than the other. The rocket is, by assumption, nice and symmetric. But if the rocket is flying through the air but is tilted with respect to its motion, its center line is at an angle with respect to the direction of its motion, then that angle, alpha, is called the angle of attack, and it's not 0. And if the angle of attack of the rocket is not 0, then it makes sense that there can be a lift force pushing the rocket to the side. Now, a lift is very important, of course, to anything that has wings or anything that is pushed through the air with a propeller. It's the lift force that counterbalances weight in an airplane in level flight, and it's also a little bit less obviously the way that a rotating propeller pushes against the outside air. For rockets, the key thing about lift is that it determines the stability of the rocket in flight. And stability is a big deal. Let's suppose we have a stick with a mass m, and so its weight is mg. That's a force, mg, that points downward due to the gravitational pull of the Earth. But in fact, that force acts on all parts of the stick. What's really happening is that every small piece of the stick has its own mass and therefore its own weight, and all those weight vectors are pointing downward, and just the total weight is mg. But the weight force is acting all along the stick. Now, suppose we want to suspend the stick by applying an upward force, by holding it up, by perhaps hanging it from a string. We want to exert a force, mg, to counter the weight of the stick. But where do we apply that force? If we apply that force on the left end of the stick, then of course the stick will rotate. There'll be enough upward force to suspend the stick, but the stick won't stay still. The stick will rotate. And in a similar way, if we apply that force over to the right, then the stick will again rotate. It will not be in balance. But if we apply that force in the middle, then we're fine. The stick can stay suspended. What this means is that there's a point along the stick called the center of gravity. And the gravitational force on the stick acts on all the parts of the stick, but it acts as if all of the weight is applied at one point, the center of gravity point. And that's the point we need to balance it. So for the stick, it's a point in the center. To balance the weight without any rotation, we'll apply our upward force there. But of course, the center of gravity is not always in the middle of the stick. So for example, if the stick had a big mass on one end, the center of gravity would be shifted over toward it. It's a sort of average position of the gravitational force along the stick, and the right-hand end has more gravitational force, more weight. So it depends on how the mass is distributed along the stick. And now, here's an important point. The center of gravity is the same thing as something called the center of mass, because the gravitational force affects all different masses in exactly the same way. They have exactly the same gravitational acceleration. And so the center of gravity, which we get by balancing the object, is the same as the center of mass, which would make sense even if there were no gravity. It would make sense out in empty space. And the center of mass has another important significance as well. The center of mass forms a kind of natural pivot point for an object's rotation. So let's just consider the motion of an object in free space without any other forces acting on it. The center of mass of the object follows a straight line path at a constant velocity, according to Newton's first law. In other words, that law of inertia, Newton's first law, applies to the center of mass of the object. And if the mass is moving subject to gravity, then it's the center of mass that follows a ballistic path. But in addition to that, the object tends to rotate about its center of mass. So we can imagine a spaceship out in free space, and that spaceship will be rotating perhaps, and if it's rotating about its center of mass. So here's a real example of that. This is actually the command and service module of the Apollo 14 mission as photographed from the lunar module, which accounts for the slight shakiness of the video. And we can see how the center of mass, following its ballistic orbit about the moon, is stationary in the image, but the spacecraft rotates about the center of mass. It's the natural pivot point. Let's imagine that we're hanging a picture on the wall. Now, we're going to hang it on a single nail, and once we hang the picture on the nail will form a pivot point, a point about which the picture is free to rotate. And so we have a fixed rotational pivot point for the picture on the wall. Now, the first thing we notice when we do this is that the nail needs to be along the center line, a vertical line that goes through the center of mass of the picture, because otherwise the picture will tilt. So let's imagine that we're putting the nail along that center line so that we can hang the picture up without it tilting. Suppose we put the nail below the center of mass. Then if the picture were exactly upright, everything would be fine. The nail would be supporting the picture. But if the picture were tilted at all, even a fraction of a degree, then what would happen is the picture would completely turn upside down. Or it might even fall off the wall. The point is that the picture is unstable if the nail is below the center of mass. Conversely, if we put the nail above the center of mass, then everything's fine if the picture is perfectly upright. But if the picture is not perfectly upright, if there's a little bit of angle to it, that will just cause the picture to wobble a bit. It will come back to being upright. The net effect of the placement of the nail is that the picture is stable. If it's a little bit off from being perfectly vertical, it tends to return to being perfectly vertical. The point here is that there are two different forces acting. The force of the nail holding the picture up and the force of gravity on the picture, which acts as if it were all acting at the center of mass of the picture. And that means that it matters where we put the nail, because if we put the nail in one place, the picture is unstable. But if we put it in another place, the picture is stable. Which brings us to the subject of aerodynamic stability. So let's imagine that we have a rocket. Let's have it be launching from the ground, so it's moving upward. And let's imagine that it's not moving quite straight. Its angle of attack is small, but not zero. That means there will be aerodynamic lift, which of course will be acting sideways since it acts perpendicularly to the velocity of the rocket. And so the aerodynamic lift acts all along the rocket body. Every part of the rocket body contributes to the lift. The nose cone, the body of the rocket, the fins at the back. But in fact, all of that lift acts as if the total lift force is applied at a particular point, the center of pressure, which is like the center of gravity for the weight of the object. And so it's as if all of the lift force is acting at this one point, the center of pressure. This means that the lift force, depending on where the center of pressure is, the lift force can cause the rocket to rotate about its center of mass. So let's consider two situations about the center of mass and the center of pressure. Let's suppose first that the center of pressure is actually located behind the center of mass. And the rocket is going upward, and it's tilted at an angle of attack alpha. Now, the lift force acts sideways. In the diagram, it acts to the left. And so that lift force tends to make alpha, the angle of attack, smaller. It tends to line the rocket up with its velocity. And so the rocket is aerodynamically stable. A small angle of attack tends to straighten itself out. But now let's suppose that the rocket has a different shape, a different distribution of mass. Maybe the fins are located in a different place, so that the center of pressure of the rocket is actually located in front of the center of mass. Then the lift force, again, acting to the left in this diagram, will tend to make the angle of attack larger. It will tend to push the rocket more and more off of the line of its velocity. And so a small deviation from being perfectly lined up will tend to become larger. In other words, the rocket is aerodynamically unstable. It's very important that our rocket is aerodynamically stable. Here's why. Let's suppose we're launching a rocket from the ground. We're launching it upward, it's under thrust. What happens? Well, there will be small tilts to the rocket. There'll be small angles of attack that will happen simply by chance, due to the wind or to fluctuations in the way the engine is firing and so on. So you will get small variations in the angle of attack. If the rocket is stable, those small variations will tend to be straightened out by the aerodynamic lift force on the rocket. So the rocket will tend to go pretty straight. But now suppose the center of pressure is located in front of the center of mass, and the rocket is aerodynamically unstable. Then those small fluctuations in the angle of attack will become quite large ones, and the rocket is literally unpredictable. You can't tell where it's going to go. So it's very important for the center of pressure to be behind the center of mass in the rocket, making it aerodynamically stable. And this, of course, is why we put the fins at the back end. Here's another good example. An arrow, like you would shoot from a bow, is designed to be very aerodynamically stable so that it will fly straight and true. And it does this, it achieves this stability in two ways. First of all, at the tail end, there's fletching, tail feathers, that can provide lift and therefore move the center of pressure toward the rear of the arrow. And then at the front of the arrow, we have a heavy arrowhead that moves the center of mass forward. So, therefore, the center of pressure is behind the center of mass, and the arrow becomes stable. Now, to do this, we need at least 3 tail feathers. Either 4 tail feathers or 3 tail feathers. Just 2 tail feathers on opposite sides will not be enough to maintain stability. Most arrows have 3 tail feathers. Let's think about what would happen if we removed two of the fins on this model rocket. Let's suppose that the yellow fins are still there, but the blue fins have been taken away. Well, then the rocket would still be stable to variations in the angle of attack in this direction, because the yellow fins would still be there to provide the lift needed to straighten the rocket back out. But a variation like this would no longer have these back fins to provide the lift necessary to straighten the rocket out. So it would be stable in some directions, but not in others. And once again, the motion of this rocket would be quite unpredictable. There are other ways to stabilize a rocket in flight through the air. And one of the ways is to use the force of drag to stabilize it. You would do that with a drogue chute. It's a small parachute that you stream out behind your craft, and just the force of drag on the parachute causes the vehicle to be straightened out. Now, of course, it also causes the vehicle to be slowed down. So this is not necessarily what you'd want to do when you were launching a rocket. Drag a parachute behind you, that would slow you down. But if you're, say, re-entering the atmosphere, as in this test for NASA's Orion spacecraft, then a drogue chute may be just the ticket to stabilizing your flight through the atmosphere. And the other way you might do it is by using rocket thrust in a very active way to guide your spacecraft and keep small variations in the angle of attack from getting too big. And these might be guided by a gyroscope. And this is something that was pioneered, of course, by Robert Goddard back in the 1930s. And these rockets actively steer at all times by redirecting their thrust, which of course is at the back of the rocket. So this is a tricky business. It's about like trying to balance a stick with your hand. You have to continually make small adjustments in order to keep the stick more or less vertical. And so that brings us to a very important question. How do we determine the stability of our rocket, the aerodynamic stability of our rocket, before we launch it? Once we launch it, it's too late. If it's unstable, we won't be able to control where it goes. And there are basically two ways of doing that. One way is to do mathematics. We could do, for example, theoretical calculations of the aerodynamics of the rocket. Now, the nicest, easiest way to understand that is to use something called the Barrowman equations. These were devised by James Barrowman, who was a graduate student in aerospace engineering back in the 1960s. And he said you could calculate the center of pressure of a rocket like calculating the center of mass of the rocket. In the case of the center of mass, you take a kind of weighted average of the locations of all the different parts of the body. And in the same way, for the center of pressure, you can take a kind of weighted average of the locations of the lift forces produced by the nose, the body, the fins, and so on. And from that, you can get the approximate location of the center of pressure. Now, the Barrowman equations are extremely useful, and they're used for small rockets and even pretty substantial sounding rockets all the time. But they're really not quite exact enough for a really big, fast rocket. And so to do theoretical calculations, you'd be forced to fall back on a giant computer simulation. And this can be something that could be simple enough to be run on a laptop, but it could also be a kind of computational simulation that would require a large supercomputer to run. So if you don't do a mathematical approach, or if you want to supplement your mathematical approach, you can also test your rocket in a wind tunnel. So what a wind tunnel does is lets you leave the rocket at rest, but have the airflow at high speed past it. So you have the airflow going to the right, and then in that smooth airflow, you hang a rocket model suspended by its center of mass in the airflow. And then you simply observe how the rocket behaves. You observe how does the rocket tend to rotate in the airflow? And of course, there are three possibilities. It may be that the rocket tends to rotate so that its nose goes into the wind, and that would mean that the center of pressure of the rocket is behind the center of mass, and the rocket will be stable in flight. But you also might observe that the rocket noses away from the wind. If it's if it has a slight angle of attack, it would tend to go farther away from the wind. And so that means that the center of pressure is in front of the center of mass, and the rocket is unstable. And if neither is true, if the rocket is equally happy to fly at any angle in the wind, then the center of pressure and the center of mass are actually at the same point, and you're neither stable nor unstable. You have neutral stability. Now, of course, the size of the rocket model and the airflow are not exactly like the full-size rocket in flight through the air. And if the airspeeds are pretty slow and the rocket model is not too small, this doesn't matter much. But it will matter if we're talking about supersonic or hypersonic speeds. Then you have to have a very powerful wind tunnel that would allow you to send your air at Mach 2 or 3 or 4, even 6 or 7. Fortunately, for model rockets, we never approach the speed of sound. And even for large rockets, the first part of their flight is fairly low speed. Here is our wind tunnel. It's not fancy, but it does give us some useful information. So it's made of cardboard. You see, it sort of tapers down to this end. At that end is the air source, which is just a simple box fan that we bought at Walmart. And then the air from that speeds up a bit as it gets to the narrow region here and blows out the front. Let's turn it on. The one problem is that the box fan produces very turbulent air. So if I lower this thread, you can see that the string is whipping around quite a bit. That's because the air coming out of the fan is very turbulent. It's stirred up by the blades. So to get a much smoother airflow, we insert this set of tubes that we've made out of paper, and we put it in here, and the tubes straighten out the airflow so that if I hold this string in the airflow, we see that it's much steadier, that it's much it's not nearly as turbulent. The turbulent whirls and eddies have been sort of straightened out by the tubes. So, how fast does our wind tunnel make the air go? Well, I happen to have with me here my airspeed meter. Let's see if I can turn it on here. There we go. And if I hold this in the flow, then I get about 3.7 meters per second, which is running speed. Okay. So let's see if we can use our wind tunnel to get some information about the stability of a rocket design. So here's what I've done. I've taken a rocket model and I have attached strings to it, and the strings are hanging from a little ring here, and the point of attachment, the place where I'm holding it, is directly above the center of mass of the rocket. So it's free to swing around the center of mass at the end of the string. So now I'll take the string and I'll hold it down into the airflow, and I'll start the rocket pointing off in some other direction. But I see that the rocket straightens itself up and noses into the airflow. If I start it in some other angle, it straightens up. The center of pressure is behind the center of mass, and that means that the rocket is aerodynamically stable. It's aerodynamically stable in this direction, Of course, if the rocket were flying backwards, then the center of pressure would be behind the center of mass. I wonder what would happen then? Well, what happened is the rocket would turn around, so it would go nose into the airflow from the wind tunnel. This rocket design is stable. So that's pretty much it. In class, we'll do more experiments with our wind tunnel and look at the aerodynamic stability of different possible rocket designs. And of course, we'll also use the wind tunnel to test the stability for any model rockets that we want to build or fly. All right, I'll see you in class.